different sizes because you've just put this random sugar, you've just brute force made lots of drops. I want to show you how to make drops that look like this. Every one exactly the same. Every one completely identical. So how can we do it? Well, we invented a new kind of microfluidics. Again, you'll see if you follow just the theme of what I tell you about is in our group we like to do things very simply because we like to focus on the science, focus on what we can do, and keep everything, all the experiments, as simple as we can make them. So we wanted to make some very, very simple devices. So we didn't, to start with this, we didn't start with the traditional kind of microfluidic device. Rather, we started with a new kind of device that's a very, very simple device. It's based just on using capillary tubes. So we go to our friends in the biology department, particularly the ones who do patch clamping, who make measurements of the cellular potential, electric potential on cells, who do patch clamping. They know how to work with these capillary devices. And we designed a new kind of microfluidic device based on them. So literally, we took capillary tubes. These are capillary tubes. These are 1 millimeter outer diameter, perfectly cylindrical, very uniform, and they're about a 0.5 millimeter inner diameter. Both the outer and the inner diameters are perfectly well defined, and these are very commonly used. What you do, they're glass, so you just heat them up in the middle. Heat them up and then pull them apart until they break. And you can make a very, very small orifice here. You can take something that had a 0.5 millimeter diameter, and you can make orifices, if you want, as thin as 1 micron in diameter. You can't see this here because this is taken with a camera, but I'll show you microscope images soon to do this. In fact, these are so common and so easy to make that there are machines that do this, and they will perfectly reproducibly. So you just go to your friends in the biology department. You say, oh, I'll buy you a cup of coffee if you'll lend me your machine. You buy them a cup of coffee, and they come back and they show you how to use the machine. It's really simple. And you can make these devices very simply. And then we want to align them. So we have to figure out, again, a very simple way to align them. And you'll see in a minute why I want to align them. But I want to do something that's very simple. So to do that, I use actually an inspiration from a toy that I had when I was a kid. I don't know if you have that in Hong Kong, but we did, where I grew up, you had this all the time. It was just a block of wood, a beautiful carved block of wood. And in the block of wood, there were these holes cut. There was a round hole and a square hole and a rectangle. You're nodding your head. Do you have one for your kids? A triangular hole? I had one when I was a kid. So there was a blocks of it. The square fit in the square, the triangle fit in the square, the triangle, the circle fit in the circle. So the triangle, of course, won't fit in the circle, and the circle won't fit in the square, right? But if you have a circle that has the outer diameter to be exactly the same as the square, it fits perfectly. And in fact, if you adjust it, you can rest this edge and this edge against here. And now you can align, if it's a cylinder in a square, you can align it perfectly. It just lines up perfectly. And look, there's 4 spaces here that you can put a fluid. And the tube, the cylinder, remember, is neck down. It's a very narrow orifice. So if I put a fluid here and a fluid in these 4 spaces, I can bring fluids together in a very simple way. I can put one fluid in the middle and the second fluid around the outside. And this orifice now will create a stream of fluid, and that will create drops. So this is what it looks like. Here's the square capillary. You can buy these now. They're commercial. The round capillary, you put them together, you line them up. You build a device like this. Remember I said we like simplicity in the lab. It's all held together with just 5-minute epoxy. Anderson, somebody as great as him, he can make a device like this in half an hour. Really. And he can teach people how to make it in a few hours. So we teach everybody how to make these things. And this is the way it looked in the lab, connected with some pumps. We look in a microscope. And it works really well. So here's one of the devices. Now you're looking with a microscope. So the square device is up here and down here. One fluid is coming here, and a second fluid is going through the orifice of the capillary tube. This is about 10 microns in diameter. These are about 20 or 30 microns in diameter. And you can see all the drops are exactly the same, one by one by one. And they're going at, look, at 1 per second, right? Actually, that's not true. Every time I show you a movie, it's taken with a high-speed camera and slowed down. So I'm really making them more at 1,000 per second. But they're all the same. In fact, I told my students, I said, okay, well, you know, what's the variation in size? How different are they in size? And they said, oh, there are a few percent difference in size. I said, oh, good. How did you measure it? They said, well, we took these images like this. We took still images. We took a circle. We fit the circle carefully to the outside, and we measured how different the circles were that fit this thing. I said, oh, that's great. That's a good idea. What's the uncertainty of the way you measured it? Oh, they said a few percent. I said, a few percent. Well, how do you know the uncertainty in the size of a few percent? You don't know. In fact, we couldn't measure the uncertainty in the size. They're so uniform in size. They're really perfectly uniform in size. It's very difficult to measure the uncertainty. So they're a few percent, but at most a few percent. What does this remind you of? Drip, 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 drip. This is actually dripping. We call this dripping. And so we label this dripping. And why we do that is if we increase the flow rate here, you form a jet. See this jet, but you still form drops. But the difference is if let me try and hold my laser pointer where the drops are formed, and you see sometimes they're formed where my laser pointer is, but sometimes they aren't. So now when you form this jet, you still form drops, but they're not as uniform in size. They're not formed quite as uniformly, but they still form drops very well. In fact, this dripping and this jetting is something that you should be very familiar with. Did I tell you that this talk has homework problems? It does. You have to go home and do this experiment. You have to do it. This is a faucet. Just go home to your faucet, your kitchen, your bathroom, your sink in the lab, wherever you like to go, and turn it on very slowly. And you'll see that it goes drip, 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 drip. But then turn it on just a little bit more. Just a little bit more. And it'll form a jet. It'll form a stream. But adjust it just right. Watch right at the bottom. And if you get that jet adjusted just right, you'll see it always breaks up into drops before it hits the bottom. And if you find it too difficult, don't give up. Go outside and get a water hose, something that really sprays water as far as you can. And spray it, but spray it as far as you can. And you'll see it always breaks up into drops. A stream of fluid always is susceptible to break up into drops. And the reason is simple, that surface tension wants something to have as little surface as possible, and having a cylinder has more surface than a sphere, so it's always susceptible to break into drops. In fact, you can understand now what's going on very simply. Here, in this case, you're forming a drop, but the surface energy is sufficient. The surface force is sufficient. If it's small enough, it's sufficient to hold it in place. And if it grows very slowly, the surface forces are always sufficient to hold it in place until finally it gets big enough that the force of gravity overcomes the force of surface tension. And exactly at that point where these two forces are balanced, the drop breaks off and falls. And if your faucet is clean and uniform, it's always exactly the same. And that's exactly what you were seeing in the dripping case. By contrast, if it's a stream of fluid, this is always susceptible. I won't go through the physics. It's simple physics. It's always susceptible to a small indentation that grows and splits it up into two drops. You always break up into drops like that. Okay, so you can have this